An acid-base reaction is a chemical reaction that occurs between an acid and a base. Several theoretical frameworks provide alternative conceptions of the reaction mechanisms and their application in solving related problems. Their importance becomes apparent in analyzing acid-base reactions for gaseous or liquid species, or when acid or base character may be somewhat less apparent. The first of these concepts was provided by the French chemist Antoine Lavoisier, circa 1776. Acid-base definitions. Historic development. Lavoisier's oxygen theory of acids. The first scientific concept of acids and bases was provided by Lavoisier circa 1776. Since Lavoisier's knowledge of strong acids was mainly restricted to oxoacids, such as HNO3 and H2SO4, which tend to contain central atoms in high oxidation states surrounded by oxygen, and since he was not aware of the true composition of the hydroallic acids, he defined acids in terms of their containing oxygen, which in fact he named from Greek words meaning acid former, meaning acid, or sharp, and gamma epsilon iota nu omicron mu alpha iota meaning engender. The Lavoisier definition was held as absolute truth for over 30 years, until the 1810 article and subsequent lectures by Sir Humphry Davy in which he proved the lack of oxygen in H2S, H2Te, and the hydroallic acids. However, Davy failed to develop a new theory, concluding that acidity does not depend upon any particular elementary substance, but upon peculiar arrangement of various substances. One notable modification of oxygen theory was provided by Berzelius, who stated that acids are oxides of nonmetals while bases are oxides of metals. Liebigs' hydrogen theory of acids circa 1838. Justus von Liebig proposed that an acid is a hydrogen-containing substance in which the hydrogen could be replaced by a metal. This redefinition was based on his extensive work on the chemical composition of organic acids, finishing the doctrinal shift from oxygen-based acids to hydrogen-based acids started by Davy. Liebig's definition, while completely empirical, remained in use for almost 50 years until the adoption of the Arrhenius definition. Arrhenius theory. The first modern definition of acids and bases was devised by Svante Arrhenius, a hydrogen theory of acids. It followed from his 1884 work with Friedrich Wilhelm Ostwald in establishing the presence of ions in aqueous solution and led to Arrhenius receiving the Nobel Prize in Chemistry in 1903. As defined by Arrhenius, an Arrhenius acid is a substance that dissociates in water to form hydrogen ions, that is, an acid increases the concentration of H+ ions in an aqueous solution. This causes the protonation of water, or the creation of the hydronium ion. Thus, in modern times, the symbol H+ is interpreted as a shorthand for H3O+, because it is now known that a bare proton does not exist as a free species in aqueous solution. An Arrhenius base is a substance that dissociates in water to form hydroxide ions, that is, a base increases the concentration of O- ions in an aqueous solution. The Arrhenius definitions of acidity and alkalinity are restricted to aqueous solutions, and refer to the concentration of the solvent ions. Under this definition, pure H2SO4 and hydrogen chloride dissolved in toluene are not acidic, and molten NaOH and solutions of calcium amide in liquid ammonia are not alkaline. Overall, to qualify as an Arrhenius acid, upon the introduction to water, the chemical must either cause, directly or otherwise, an increase in the aqueous hydronium concentration, or a decrease in the aqueous hydroxide concentration. Conversely, to qualify as an Arrhenius base, upon the introduction to water, the chemical must either cause, directly or otherwise, a decrease in the aqueous hydronium concentration, or an increase in the aqueous hydroxide concentration. The reaction of an acid with a base is called a neutralization reaction. The products of this reaction are a salt and water. acid plus base, salt plus water. In this traditional representation, an acid-base neutralization reaction is formulated as a double replacement reaction. For example, the reaction of hydrochloric acid, hydrogen chloride, with sodium hydroxide, NaOH, solutions produces a solution of sodium chloride, NaCl, and some additional water molecules. Hydrogen chloride plus NaOH, NaCl plus H2O. The modifier in this equation is important. It was implied by Arrhenius, not included explicitly. It indicates that the substances are dissolved in water. In fact, though all three substances, hydrogen chloride, NaOH and NaCl, are capable of existing as pure compounds, in aqueous solutions they are fully dissociated into the ions H+, Cl, Na+, and O. Bronsted-Lowry definition. The Bronsted-Lowry definition, formulated in 1923, independently by Johannes Nicolaus Bronsted in Denmark and Martin Lowry in England, is based upon the idea of protonation of bases through the deprotonation of acids, that is, the ability of acids to donate hydrogen ions, otherwise known as protons, to bases which accept them. An acid-base reaction is, thus, the removal of a hydrogen ion from the acid and its addition to the base. The removal of a hydrogen ion from an acid produces its conjugate base, which is the acid with the hydrogen ion removed. The reception of a proton by a base produces its conjugate acid, which is the base with the hydrogen ion added. Unlike the previous definitions, the Bronsted-Lowry definition does not refer to the formation of salt and solvent, but instead to the formation of conjugate acids and conjugate bases, produced by the transfer of a proton from the acid to the base. In this approach, acids and bases are fundamentally different in behavior from salts, which are seen as electrolytes. Subject to the theories of Debye, Onsager, and others, an acid and a base react not to produce a salt and a solvent, but to form a new acid and a new base. The concept of neutralization is thus absent. Bronsted-Lowry acid-base behavior is formally independent of any solvent, making it more all-encompassing than the Arrhenius model. The general formula for acid-base reactions according to the Bronsted-Lowry definition is Ha plus B BH plus A minus, where Ha represents the acid, B represents the base, BH plus represents the conjugate acid of B, and A minus represents the conjugate base of Ha. For example, a Bronsted-Lowry model for the dissociation of hydrochloric acid in aqueous solution would be the following. Hydrogen chloride plus H2OH3O plus Cl minus. The removal of H plus from the hydrogen chloride produces the chloride ion, Cl minus, the conjugate base of the acid. The addition of H plus to the H2O forms the hydronium ion, H3O plus, the conjugate acid of the base. Water is amphoteric, that is, it can act as both an acid and a base. The Bronsted-Lowry model explains this, showing the dissociation of water into low concentrations of hydronium and hydroxide ions. H2O plus H2OH3O plus O minus. This equation is demonstrated in the image below. Here, one molecule of water acts as an acid, donating an H plus and forming the conjugate base, O minus, and a second molecule of water acts as a base, accepting the H plus ion and forming the conjugate acid, H3O+. As an example of water acting as an acid, consider an aqueous solution of pyridine, C5H5N. C5H5N plus H2O, C5H5NH plus O minus. In this example, a water molecule is split into a hydrogen ion, which is donated to a pyridine molecule, and an hydroxide ion. In the Bronsted-Lowry model, the solvent does not necessarily have to be water. For example, consider what happens when acetic acid, CH3COOH, dissolves in liquid ammonia. CH3COOH plus NH3NH plus 4 plus CH3COO minus and H plus ion is removed from acetic acid, forming its conjugate base, the acetate ion, CH3COO minus. The addition of an H plus ion to an ammonia molecule of the solvent creates its conjugate acid, the ammonium ion, NH4+. The Bronsted-Lowry model calls hydrogen-containing substances acids. Thus, some substances, which many chemists consider to be acids, such as SO3 or BCl3, are excluded from this classification due to lack of hydrogen. Gilbert N. Lewis wrote in 1938, to restrict the group of acids to those substances that contain hydrogen interferes as seriously with the systematic understanding of chemistry as would the restriction of the term oxidizing agent to substances containing oxygen. Furthermore, Co and KNH2 are not considered Bronsted bases, but rather salts containing the bases O- and NH2-. Lewis' definition. The hydrogen requirement of Arrhenius and Bronsted-Lowry was removed by the Lewis definition of acid-base reactions, devised by Gilbert N. Lewis in 1923, in the same year as Bronsted-Lowry, but it was not elaborated by him until 1938. Instead of defining acid-base reactions in terms of protons or other bonded substances, the Lewis definition defines a base to be a compound that can donate an electron pair, and an acid to be a compound that can receive this electron pair. For example, boron trifluoride, BF3, is a typical Lewis acid. It can accept a pair of electrons as it has a vacancy in its octet. The fluoride ion has a full octet and can donate a pair of electrons. Thus BF3 plus F minus BF4 minus is a typical Lewis acid, Lewis base reaction. All compounds of group 13 elements with a formula AX3 can behave as Lewis acids. Similarly, compounds of group 15 elements with a formula DY3, such as amines, NR3, and phosphines, PR3, can behave as Lewis bases. Adducts between them have the formula X3ADY3 with a dative covalent bond, shown symbolically as between the atoms A and D. Compounds of group 16 with a formula DX2 may also act as Lewis bases. In this way, a compound, like an ether, R2O, or a thioether, R2S, can act as a Lewis base. The Lewis definition is not limited to these examples. For instance, carbon monoxide acts as a Lewis base when it forms an adduct with boron trifluoride, of formula F3BCO. Adducts involving metal ions are referred to as coordination compounds. Each ligand donates a pair of electrons to the metal ion. The reaction Ag4 plus 2NH3 Ag2 plus 4H2O can be seen as an acid-base reaction in which a stronger base replaces a weaker one. The Lewis and Bronsted-Lowry definitions are consistent with each other since the reaction H plus O minus H2O is an acid-base reaction in both theories. Solvent system definition. One of the limitations of the Arrhenius definition is its reliance on water solutions. Edward Curtis Franklin studied the acid-base reactions in liquid ammonia in 1905 and pointed out the similarities to the water-based Arrhenius theory. Albert F. O. German, working with liquid phosgene, COCl2, formulated the solvent-based theory in 1925, thereby generalizing the Arrhenius definition to cover aprotic solvents. German pointed out that in many solutions, there are ions in equilibrium with the neutral solvent molecules. Solvonium, a generic name for a positive ion. Solvate, a generic name for a negative ion. For example, water and ammonia undergo such dissociation into hydronium and hydroxide, and ammonium and amide, respectively. 2H2OH3O++O- 2NH3NH+4+NH-2. Some aprotic systems also undergo such dissociation, such as dinitrogen tetroxide into nitrosonium and nitrate, antimony trichloride into dichloroatimonium and tetrachloroantimonate, and phosgene into chlorocarboxonium and chloride. N2O4 NO++ NO -32 SbCl3 SbCl plus 2 plus SbCl -4 COCl2 COCl plus Cl minus. A solute that causes an increase in the concentration of the solvonium ions and a decrease in the concentration of solvate ions is defined as an acid. A solute that causes an increase in the concentration of the solvate ions and a decrease in the concentration of the solvonium ions is defined as a base. Thus, in liquid ammonia, KNH2 is a strong base, and NH4NO3 is a strong acid. In liquid sulfur dioxide, thionyl compounds behave as acids, and sulfites behave as bases. The non-aqueous acid-base reactions in liquid ammonia are similar to the reactions in water. 2NaNH2 plus zinc 2 Na2 zinc 4 2NH4I plus zinc 2 zinc 4 I2 nitric acid can be a base in liquid sulfuric acid. HNO3 plus 2H2SO4 NO plus 2 plus H3O plus 2HSO minus 4. The unique strength of this definition shows in describing the reactions in aprotic solvents. For example, in liquid N2O4, AgNO3 plus NOCl N2O4 plus AgCl. Because the solvent system definition depends on the solute as well as on the solvent itself, a particular solute can be either an acid or a base depending on the choice of the solvent. HClO4 is a strong acid in water, a weak acid in acetic acid, and a weak base in fluorosulfonic acid. This characteristic of the theory has been seen as both a strength and a weakness, because some substances have been seen to be acidic or basic on their own right. On the other hand, solvent system theory has been criticized as being too general to be useful. Also, it has been thought that there is something intrinsically acidic about hydrogen compounds, a property not shared by non-hydrogenic solvonium salts. Lux flood definition. This acid-base theory was a revival of oxygen theory of acids and bases, proposed by German chemist Hermann Lux in 1939. Further improved by Haken-Flood circa 1947, and is still used in modern geochemistry and electrochemistry of molten salts. This definition describes an acid as an oxide ion acceptor and a base as an oxide ion donor. For example, MgO plus CO2 MgCO3 Cal plus CO2 CaCO3 No minus 3 plus S2O2 minus 7 No plus 2 plus 2 SO2 minus 4. Usanovich definition. Mikhail Usanovich developed a general theory that does not restrict acidity to hydrogen-containing compounds. But his approach, published in 1938, was even more general than Lewis' theory. Usanovich's theory can be summarized as defining an acid as anything that accepts negative species or donates positive ones, and a base as the reverse. This defined the concept of redox as a special case of acid-base reactions. Some examples of Usanovich acid-base reactions include Na2O plus SO3 2 Na plus SO2 minus 4 3 2S plus Sb2S5 6 NH plus 4 plus 2 SBS3 minus 4 2 Na plus Cl2 2 Na plus 2 Cl minus. Pearson definition in 1963. Ralph Pearson proposed a qualitative concept known as hard-soft acid-base principle, later made quantitative with help of Robert Parr in 1984. Hard applies to species that are small, have high charge states, and are weakly polarizable. Soft applies to species that are large, have low charge states, and are strongly polarizable. Acids and bases interact, and the most stable interactions are hard-hard and soft-soft. This theory has found use in organic and inorganic chemistry. Acid-base equilibrium. The reaction of a strong acid with a strong base is essentially a quantitative reaction. For example, hydrogen chloride plus NaH2O plus NaCl. In this reaction, both the sodium and chloride ions are spectators as the neutralization reaction. H++ O minus H2O does not involve them. With weak bases, addition of acid is not quantitative because a solution of a weak base is a buffer solution. A solution of a weak acid is also a buffer solution. When a weak acid reacts with a weak base, an equilibrium mixture is produced. For example, adenine, written as R, can react with a hydrogen phosphate ion, HPO42-R plus HPO42-A- plus H2PO4-. The equilibrium constant for this reaction can be derived from the acid dissociation constants of adenine and the hydrogen phosphate ion. R equals Ka1, A minus, H plus, H2PO4 minus, equals Ca2, HPO42 minus, H plus. The notation X signifies concentration of X. When these two equations are combined by eliminating the hydrogen ion concentration, an expression for the equilibrium constant is obtained. R HPO42 minus equals Ka minus H2PO4 minus K equals Ca1. Ca2 acid-alkali reaction. An acid-alkali reaction is a special case of an acid-base reaction, where the base used is also an alkali. When an acid reacts with an alkali, it forms a metal salt and water. Acid-alkali reactions are also a type of neutralization reaction. In general, acid-alkali reactions can be simplified to O minus plus H plus H2O by emitting spectator ions. Acids are in general pure substances that contain hydrogen ions or cause them to be produced in solutions. Hydrochloric acid and sulfuric acid are common examples. In water, these break apart into ions. Hydrogen chloride H++ Cl minus H2SO4 H++ HSO minus 4 to produce hydroxide ions in water. The alkali breaks apart into ions as below.